Hi everyone, welcome back. This is the part 2 video for section 3.1. I'm here at the bottom of page 6 and we're going to talk about probability in genetics. So a little bit of a background or an introduction here tells us that Gregor Mendel, an Austrian monk, used the idea of randomness to establish the study of genetics. To study the flower color of certain pea plants, he found that pure red crossed with pure white produces red. This leads us to the concept in genetics of what are called dominant and recessive genes. So Mendel theorized that red is dominant, symbolized by capital R, while white is recessive, symbolized by lowercase r. The pure red parent carried only genes for red, and the pure white parent carried only genes for white. Now, I'm going to show you a breakdown of these results on the next slide, and then they'll ask us some questions. If any of you have ever taken a biology course, maybe just like Bio 101, you might be familiar with this type of probability already. I'm going to go ahead and turn to page 7 and show you the information in table form. Every offspring receives one gene from each parent, which leads to the table below. Every second generation is red because R is dominant. So imagine the first to second generation. So the first parent is pure red and the second parent is pure white. Now when you cross those together, every offspring is half and half, a red and a white gene. Because the red genes are dominant, all of the offspring in that first to second generation will end up red. It's more interesting to see what happens from going from the second to third generation, because now the first parent has one of each gene, the red and the white. Likewise here, the second parent has a red and a white. Now when you put those together, you can get a pure red or a pure white. Or you can get a mixture of each, RR and RR. Now, both of these will end up being red because red is the dominant gene. Now, if you look at the following slide, they ask us a couple of probability questions, referring to the second to third generation table on that previous slide. So we want to look at this table over here to the right. This is the one we're going to use to answer their probability question. Pardon me. They ask us to determine the probability that a third generation will be red or white. So if you look, we're talking about the offspring results. See if I can fit everything in the frame here. Talking about the offspring results in this third generation. So the probability that the offspring in this third generation end up red, notice there's 3 out of 4, because any of them that have the uppercase R will end up being red in color. Even though they're not necessarily pure red, right? Like even the ones that have the white gene, they'll still show up as red colored plants. So in this case, I'm going to go ahead and list out the probability as 3 out of 4, or 75%. And again, that's the pure red offspring or either of the offspring that have the red gene. That's the dominant. There's only a 1 in 4 chance that offspring in the third generation ends up being white colored, right? That means they have both of the white genes present. You may have seen the very, very common type of probability in genetics. You could do this with eye color. Sometimes it's done with, for example, another classic example of this is cystic fibrosis and how that's passed from one generation to the next, and on and on and on. All right, we've got one more concept to deal with in section 3.1. It's going to start at the top of page 8, and we're going to talk about the odds of an event. Odds compare the number of favorable outcomes to the number of unfavorable outcomes. Odds are commonly quoted in horse racing, lotteries, and most other gambling situations. You'll often hear people talking about odds in real life rather than probabilities. They'll say, well, what are the odds of this? What are the odds of that? It gives us the same type of information as probability. It's just presented a little bit differently. So let's go ahead and get a little bit more specific with the definition, and then we'll start seeing some examples. If all outcomes in a sample space are equally likely, A of them are favorable to the event E, and the remaining B outcomes are unfavorable to that event, then the odds in favor of E are A to B. That's a ratio, and you can write it as A to B, or you can write it as A colon B, that's also a ratio, or you can write this as the fraction A over B. This is the same different representations you have in arithmetic to represent ratios. The odds against E are just backwards. This would be the number of unfavorable outcomes compared to the favorable. And again, you could write that with the word to. You could write it with the colon, B to A, or you could write it as a fraction, B over A. So all of those are correct interpretations or representations. Again, the key is to look on MyMathLab to see how they're wanting you to express it. Most likely, they're going to be wanting the answers represented as fractions. So that's what I'm going to show you in the actual example sets. Let's go ahead and turn over to page 9, and we'll start looking at some of these odds examples. So I'm at the top of page 9. It tells us here that 200 tickets were sold for a drawing to win a new television. If Matt purchased 10 of the tickets, what are the odds in favor of Matt's winning the television? Now, again, notice that this is a slightly different way to phrase a probability question. Instead of simply saying, what's the probability that Matt wins this TV? They're saying, what are the odds in favor of Matt's winning the television? So there's two things to figure out. How many favorable outcomes are there? Compare that to how many unfavorable outcomes there are. So if you look, if Matt purchased 10 of the tickets, so a favorable outcome is his ticket being selected. So there's 10 ways that can happen. He's got 10 tickets in this raffle. That means the other 190 are unfavorable. Notice the favorable and unfavorable together add up to the total number of outcomes. This is the same concept we had in counting and set theory, known as the complement. These will always add up to the total. So the odds in favor are going to equal 10 out of 190. Of course, we can reduce that and say that's 1 to 19 odds. A lot of times in real life when people talk about odds, they'll actually talk about the odds against, the odds, like in this case, of not winning. So you might see something in real life and they'll say, oh, well, the odds of that are 19 to 1. Well, that's actually the odds against a favorable outcome. These are the odds in favor of winning the television. 1 to 19 are the odds. That's not a probability. These are the odds. For the next one, they tell us to suppose that the probability of rain today is 0.43 or 43%. Give this information in terms of odds. So start with the fact that the probability of rain, they tell us, is 0.43. Now I'm going to convert that to a fraction. That's 43 hundredths. So when I write it as a fraction, it's 43 out of 100. Now remember, when we look at probability, we're talking about the favorable compared to the total. So this is favorable for rain, and 100 is our total. That means no rain. Just think about the complement. 43 and 57 add up to 100, so no rain outcomes would be 57. Now that we have favorable to rain and not favorable to rain, we can go ahead and make comparisons based on odds. So let's start with odds in favor of rain. I would just take the number of outcomes favoring rain, which in this case is 43, divided by the number of outcomes not favoring rain, which in this case is 57. So 43 to 57, those are the odds. And 43 is a prime number, so that fraction does not reduce, and I'm going to leave it as is. Now, the other way, because they don't really specify how they want it, they just say write it in terms of odds. So there's the odds in favor of rain. Here are your odds against rain. Just take the no rain outcomes, which in this case is 57, and divide it by the number of rain outcomes, which in this case is 43. My point is, when you're talking about odds, you can really express it one way or the other. You would just have to be looking and seeing what they want us, what they want us to write in the problem. Here they didn't specify, so I showed you both. All right, let's go ahead and turn to page 10. I think I've got one last example to share with you here. And this is where we're going to convert from odds back to probability. Your odds of completing college algebra class are 16 to 9. Based on that, what is the probability you will complete the class? We'll start with the odds of completing college algebra, 16 to 9. So based on how this is phrased, I have 16 outcomes where we will complete the course and 9 outcomes of not completing the course. So notice 16 and 9, that's 25 outcomes total. I'm saying outcomes, you could also think of these as students. 16 of them successfully complete the course, 9 of them do not. So 16 to 9, that indicates 25 students total. So now you can look at the probability that a student will complete a college algebra course. Take the number of successful outcomes, there's 16 students that will complete the course, out of the total number of students in that course. 16 out of 25. Since this is a probability, it would be appropriate to write it as a decimal or even a percentage. So we'll take 16 divided by 25. That works out to 0.64, or if you prefer a percentage, 64%. So basically what I'm illustrating with those last couple of examples, if you know the odds, you can easily convert it to probability and vice versa. So that does it for section 3.1, which are just the basic concepts of probability. Once you're comfortable with the material, go ahead and try out the problems on MyMathLab. And as always, if you're having any questions or you need a little help, please make sure to let me know.